Tonight, we're going to explore a galaxy that, on paper, should not exist. Imagine an island of stars drifting through space where everything you see is everything there is. No hidden halo, no invisible mass. Every star, every cluster, every wisp of gas moves exactly as the visible matter predicts, with no need for any dark, unseen scaffolding holding the system together. That vision cuts straight against the standard picture of the universe. In modern cosmology, dark matter is the silent architecture behind almost every galaxy. It is supposed to be the invisible framework that lets galaxies form, merge, and survive the relentless pull of gravity and the pressure of cosmic expansion. Galaxies are expected to sit inside enormous cocoons of dark matter with 5 to 10 times more dark matter than normal matter. No one predicts galaxies that simply opt out of this invisible infrastructure, and yet that is exactly what some observations seem to show. A few years ago, astronomers pointed powerful telescopes at a faint, ghostly smear near the massive galaxy NGC 1052. The target received an unassuming catalogue name, NGC 1052 DF2. But when scientists measured how fast its star clusters moved, the numbers looked wrong in the most dramatic way possible. The motions matched what you would expect from the stars alone, with almost no room left for dark matter at all. Soon after, another ultra-diffuse galaxy in the same region, NGC 1052 DF4, appeared to tell the same story. Two galaxies, both large in size but extremely faint, both apparently living without the dark matter halos that every model says they should have. No one expects galaxies this fragile to hold together in the violent gravitational environment near a massive neighbour, and absolutely no one anticipates that they would do it powered only by their visible stars. If dark matter is really the backbone of cosmic structure, how can any galaxy exist without it? Are DF2 and DF4 genuine rebels against the standard model, or are the measurements tricking us through distance errors, subtle biases, or hidden motions that current instruments cannot fully resolve? Could tidal forces have stripped away their dark matter halos during close encounters, leaving behind bare stellar skeletons? Or does their behavior hint that gravity itself might change on large scales, challenging the need for dark matter at all? Before we get started on those possibilities, it helps to know how dark matter is usually detected without ever being seen. By the end of tonight, you're going to understand how scientists read the rotation of galaxies, the random motions of star clusters, and the bending of light to infer invisible mass. Now, let's begin. The story of dark matter-free galaxies will take us right to the boundary between what the current cosmological model explains and what it might be missing. To see why these galaxies are so shocking, you need to see what the universe looks like with dark matter turned on. Imagine an invisible skeleton running through all of space. Not a few stray bones here and there, but a vast three-dimensional web, stretching far beyond the most distant planets in our own system. Dark matter is the name given to the mass that does not shine. It does not glow, it does not scatter light, it does not ride along with the solar wind like charged particles from the sun. It interacts, as far as current missions can tell, almost entirely through gravity. Yet it outweighs the normal matter in galaxies by a factor of about 5 to 10. For every kilogram of stars and gas that telescopes can see, there are several hidden kilograms that only reveal themselves through their pull. This pull matters. In the early universe, tiny fluctuations in density, minute wrinkles in the hot plasma, felt the gravity of dark matter first. Before there were planets, before there were stars, dark matter began to clump. Those clumps grew into halos, enormous cocoons of invisible mass. Within those halos, normal gas cooled, condensed, and eventually lit up as the first galaxies. The picture that emerges is clear. Galaxies do not just float in space. They are embedded in dark, matter halos from birth. Tonight, we're going to trace that idea from the smallest scales to the largest. Zoom in and dark matter keeps stars from flying apart. Zoom out and it sculpts the cosmic web, filaments, clusters, and vast empty voids in between. Simulations that include dark matter naturally produce this web, matching what large surveys have discovered when they map hundreds of thousands of galaxies across the sky. And the ratios are not subtle. In a typical spiral galaxy, the visible disk might hold a few 100 billion solar masses in stars and gas. The dark halo around it can hold 1 trillion or more. Remove that halo and everything changes. Rotation speeds drop. Stellar orbits rearrange. The elegant flat rotation curves that scientists measure, where stars far from the center move just as fast as those near the core, would collapse toward what Newtonian gravity predicts from visible mass alone. This is why dark matter is not just a patch on one odd observation. Galaxy rotation curves, the motions of galaxies inside clusters, the way massive clusters bend light from more distant systems through gravitational lensing, and the detailed pattern of temperature fluctuations in the cosmic microwave background all point independently to the same invisible component. No one predicts all of those lines of evidence to converge by accident. Absolutely no one anticipates they would agree on the same cosmic recipe. About 5% normal matter, about 27% dark matter, the rest in dark energy. So here is the tension. If dark matter is the scaffolding, galaxies are the buildings bolted to it. A normal galaxy without dark matter would be like a skyscraper with no steel beams, standing tall in a high wind. Under the current model, it should crumple, disperse, or never form in the first place. And yet, a handful of ghostly systems now appear to be doing exactly that. Before we get started on those outliers, we need to examine how a galaxy can even advertise that something is missing. A galaxy cannot raise its hand and say, "I'm full of dark matter." It only has one way to communicate: motion. Stars orbit, gas swirls, light bends. From those signals, scientists try to reconstruct the hidden architecture of mass that holds a system together. Now, let's begin with the workhorse tool, galaxy rotation curves. Take a spiral galaxy and imagine drawing a line from its center out through one of its arms. Along that line, astronomers measure how fast stars and gas clouds are orbiting at different distances from the core. They use the Doppler shift of spectral lines, turning tiny changes in wavelength into precise speeds, thousands of light years from the center. On paper, the prediction is simple. Most of the visible mass is concentrated near the bright central bulge. Move outward, and the pull of gravity from that luminous region should weaken. If only the visible stars and gas mattered, orbital speeds should rise near the center, then fall off with distance, the way planets in our own solar system slow down as they move farther from the Sun. But when the first detailed rotation curves were mapped in the 1970s and 80s, reality refused to cooperate. The speeds did not drop. They stayed flat. In many galaxies, they even rose slightly in the dim outskirts, where almost no light is seen. No one predicts that from the visible mass alone. The only way to keep those outer stars from flying off into space is to embed the galaxy in a much larger, invisible halo of matter. To picture this, think of a merry-go-round. The horses near the center can spin fast without tearing the ride apart. But if the horses at the very edge are whipping around just as fast as the inner ones, something extra must be anchoring the platform. Hidden weights, reinforced beams, extra, unseen support holding the whole system together against the centrifugal pull. Rotation curves are not the only clue. In compact star clusters and dwarf galaxies where there is no neat rotating disk, scientists measure velocity dispersion instead. How widely the speeds of individual stars are spread out. If those stars are moving more rapidly than the visible mass can confine, the invisible mass budget has to increase. Then there is gravitational lensing. When a galaxy or a cluster of galaxies sits in front of more distant background galaxies, its gravity bends their light, distorting them into arcs and smears. By measuring those distortions, astronomers weigh the total mass along the line of sight, visible and invisible together, and compare it to what the stars and hot gas can account for. Tonight, we're going to push those tools to their limits, because in a few sections, these same measurements will show something that absolutely no one anticipates. Galaxies whose motions line up almost perfectly with the visible stars, leaving no room, or almost no room, for dark matter at all. To even talk about galaxies that might lack dark matter, there's a quiet question that has to be answered first. What counts as a galaxy in the first place? Before we get started with dramatic claims, astronomers need a working definition, because if the category is fuzzy, the mystery can evaporate just by changing the label. Operationally, a galaxy is not just a pretty swirl of stars in space. It is a gravitationally bound system of stars, gas, dust, and, crucially, dark matter, all embedded in a massive invisible halo that dominates its gravity. The stars and gas are the bright frosting. The dark halo is the dense, unseen cake underneath. In the modern picture, that halo sets the boundary of the system, defines how fast stars orbit, and controls how the galaxy grows over billions of years. Now, let's begin to separate that from something that only looks similar at first glance. Star clusters, like the globular clusters orbiting the Milky Way, are also bound collections of stars. They can contain hundreds of thousands, even millions of suns. But their gravity is provided almost entirely by the stars themselves. No one expects a huge, dark halo around them. They're compact, only a few tens of light years across, and their internal motions can be explained without invoking hidden mass. The contrast is sharp. A typical dwarf galaxy might have as many stars as a large globular cluster, but spread over thousands of light years and moving under the pull of a dark halo 10 or more times more massive than all its visible material. A cluster is like a dense city block. A galaxy is like an entire continent with a deep, invisible foundation. The size, the total mass, and especially the need for dark matter to hold the system together all point to galaxy rather than cluster. This leads to a practical rule that many scientists quietly use. If the internal motions of stars and gas demand dark matter, the object is a galaxy. If they don't, it might just be a cluster. That's why the idea of a galaxy with no dark matter is so unsettling. It takes the operational definition and flips it. Designed around the assumption that dark matter is the main actor, the whole classification system suddenly has to confront a stage where the lead never shows up. And then along come the ultra-diffuse galaxies. UDGs have as many stars as small dwarfs, but those stars are spread over regions as large as the Milky Way, making them appear as ghostly smudges in deep images. huge in extent, faint in light, with stars drifting through a volume that feels almost empty. Some of these systems show motions that clearly require dark matter. Others, at first glance, seem dynamically supported, mostly, by their stars. Here's the pattern interrupt. An object the size of a big galaxy, glowing as dimly as a whisper, with internal motions that hint at little or no dark halo. If it walks like a galaxy in size and shape, but its gravity looks more like a cluster, what is it? By the end of tonight, you're going to understand why that question cuts to the core of cosmology, and why a few ultra-diffuse galaxies in particular forced scientists to ask whether the definition itself needs to be rewritten. Because next, the mission goes from definitions to data. The spacecraft are telescopes on Earth and in orbit, and they have just discovered real candidates for galaxies that seem to live beyond the dark matter rulebook. Those candidates only make sense once you know what the universe is supposed to do. In the standard picture, galaxies are not free-floating islands that just appear wherever they like in space. They are passengers locked inside invisible structures that form long before the first stars ignite. Now, let's begin. In modern cosmology, that framework is called LCDM, Lambda Cold Dark Matter. Lambda is the dark energy term that accelerates the expansion of the universe. The cold dark matter part is the invisible mass that clumps first under gravity. Long before planets, long before the solar system, even before the first galaxies, tiny fluctuations in dark matter density grow into halos, like overlapping bubbles of extra gravity. Gas falls into those halos. Hydrogen and helium, the ordinary matter left over from the Big Bang, stream towards these wells the way air would rush into a deep valley. As the gas collapses, it heats up, then cools, then fragments. Stars ignite. Over hundreds of millions of years, a galaxy takes shape in the center of the halo, built from the inside out, anchored in a massive extended cocoon of dark matter. This growth is not peaceful. The universe runs a hierarchical construction project. Small halos form first. They merge into bigger halos, which merge again, building clusters and giant galaxies. When halos collide, the galaxies inside them interact and merge too. Tidal forces stretch out long streams of stars, fling dwarf galaxies into new orbits, and pile up satellite systems around massive hosts. By the end of tonight, you're going to understand why this violence is not a side note. It is the engine that sculpts the entire cosmic web. In supercomputer simulations that follow billions of particles of dark matter, one rule emerges over and over. Every galaxy lives inside a halo. There are no exceptions. Even the faintest dwarf galaxies, systems with only a few million stars, form deep in dark matter wells. Their visible mass is tiny compared to the invisible halo, so their outer regions are expected to be overwhelmingly dark matter dominated. Baryonic physics, the realm of normal matter, certainly fights back. Supernova explosions drive powerful winds that can blow gas out of small galaxies. Star formation can rearrange the central density, puffing up the inner regions or carving shallow cores. Feedback, radiation, and gas inflows all reshape the luminous parts of a galaxy, but they do this within the gravitational boundary set by dark matter. They can stir the soup, they do not remove the pot. And that leads to the crucial implication. In LCDM, a galaxy completely devoid of dark matter is not just rare, it is, in practice, forbidden. No one expects a stable island of stars to survive without its halo. No one predicts a long-lived system where baryons have escaped their dark skeleton. Absolutely no one anticipates entire galaxies that seem to have slipped the grip of the very framework that built the cosmos. So when observations hint at such systems, the mission changes. The question is no longer how do galaxies form? It becomes, what went so catastrophically wrong with this one? So when observations hint at such systems, the mission changes. The question is no longer how do galaxies form? It becomes, what went so catastrophically wrong with this one? Before we get started with the headline cases, there's a twist. Galaxies had been misbehaving long before anyone whispered about dark matter free. Astronomers were already staring at dwarfs on the edge of the cosmic map and seeing numbers that didn't quite line up. Some tiny galaxies seemed almost pure dark matter, with stars drifting through a gravitational well far deeper than their visible light could explain. Others, with similar sizes and brightness, looked surprisingly light on dark matter, as if the invisible halo had been thinned out. In the standard picture, that shouldn't happen often. Take a galaxy's visible mass, measure how fast its stars and gas orbit, and the mismatch tells you how much dark matter is wrapped around it. For big spiral systems, the answer is stable and clear, 5 to 10 times more dark than luminous, but in dwarfs, the relationship frays. Two galaxies with the same starlight can have wildly different rotation speeds or internal velocity dispersions. The boundary between normal halo and what is going on here starts to blur. Scientists had an escape hatch for this. Galaxies do not live in isolation. They orbit larger companions, plunge through clusters, feel tidal forces that can stretch and stir their dark halos. Gas can be blown out by supernova winds. Stars can be rearranged by bars and spiral arms, and all that messy baryonic physics feeds back into the dark matter distribution. No one expects every dwarf to sit quietly in a pristine, textbook halo. That logic becomes especially tempting when tidal dwarf galaxies enter the scene. These are small systems born not from their own dark clump, but from debris flung out when big galaxies collide. Imagine two massive spirals tearing past each other, drawing long tidal tails of gas and stars into space. In simulations, those tails can fragment and collapse into new, miniature galaxies. But the dark matter, sitting in a broader, more diffuse halo, doesn't follow as easily. The result? Tidal dwarfs that are predicted to be relatively poor in dark matter compared with their more traditional cousins. For years, these outliers were filed under interesting, but manageable edge cases, special environments, complicated feedback. By the end of tonight, you're going to understand how reassuring that attitude once felt. The theory bends, but it doesn't break. Then, around 2018, the pattern interrupts. Observations emerge that push the tension far beyond a little low on dark matter. The data begin to say something far more radical. Here is a galaxy where the stars move exactly as their visible mass predicts, as if the dark halo is missing altogether. No one predicts that. Absolutely no one anticipates the moment when the usual excuses stop working. So what happens when the measurements refuse to budge and the system behaves as though dark matter simply isn't there at all? So to see what that looks like in the real universe, you have to meet one of the strangest islands of stars ever discovered. It's called NGC 1052 DF2. Astronomers just call it DF2. On deep images, it barely looks like a galaxy at all. DF2 is an ultra-diffuse galaxy, a faint smudge of space in the NGC 1052 group. In terms of physical extent, it rivals the Milky Way, tens of thousands of light-years across, a sprawling system of stars. But the number of stars is tiny. Instead of hundreds of billions, you're looking at maybe a few 100 million. Imagine stretching a small dwarf's worth of starlight over a Milky Way-sized canvas. The result is almost transparent. That transparency is the only reason DF2 was seen at all. Traditional surveys focus on bright, compact galaxies. DF2 would have slipped under the radar if not for a mission built specifically to hunt for ghosts, the Dragonfly Telephoto Array. This unusual spacecraft on the ground is a cluster of telephoto lenses working together, optimized to capture extremely low surface brightness structures around galaxies and galaxy groups. Dragonfly's deep imaging of the region around the massive elliptical galaxy NGC 1052 revealed several ultra-diffuse companions. Among them, DF2 stood out. It looked big. It looked incredibly dim, and it looked detached from the usual relationship between size and brightness that scientists expect. Before we get started on the dark matter mystery, there is one crucial number that controls everything: distance. Early analyses placed DF2 at around 65 million light-years away, the same general distance as the NGC 1052 group. That estimate matters because distance sets the scale. If DF2 is that far, its apparent size on the sky translates into a Milky Way-like diameter, and its total starlight implies a certain stellar mass. Change the distance, and you change how massive the galaxy is supposed to be, and how much dark matter it must contain to hold itself together. Then there were the star clusters. Scattered through DF2, Dragonfly and follow-up observations discovered a surprisingly rich system of bright, globular clusters, dense, ancient swarms of stars, each one a compact gravitational laboratory. For such a dim galaxy, these clusters are unusually luminous and few in number, almost like lanterns floating in a cosmic fog. Those lanterns became the key. By measuring their motions, scientists could trace DF2's gravitational field, testing how much invisible mass surrounds the visible stars. By the end of tonight, you're going to understand why that was such a dangerous question to ask. When the velocities came back, the pattern interrupt was brutal. The globular clusters were moving slowly, too slowly. For a galaxy that size, at that distance, with a normal dark halo, they should have been racing around. Instead, they drifted as though only the stars were there, and nothing beyond. No one expects a result like that from a system this large. Now, let's begin to unpack what those numbers really mean, and how one ghost galaxy ignited a new battle over dark matter itself. Those slow motions are the clue. To turn them into a verdict on dark matter, scientists had to weigh an entire galaxy using only a handful of tiny, ancient star clusters as test particles. It sounds fragile, but this is one of the sharpest tools astronomers have for probing invisible mass far beyond the solar system. Before we get started, picture what a globular cluster really is. Not a loose group of stars, but a compact sphere of hundreds of thousands of suns, all bound together, orbiting through a galaxy like bright, dense satellites. In DF2, these clusters are surprisingly luminous beacons embedded in a very faint smear of starlight, which makes them perfect targets for a different kind of mission. A spectroscopic weighing experiment. The technique is elegant. Point a large telescope at one cluster, spread its light into a spectrum, and measure how its absorption lines are shifted by the Doppler effect as it moves along our line of sight. Do this again and again for as many clusters as the spacecraft-grade instrumentation on Earth can pick out. Each radial velocity is one data point. Together, they form a velocity dispersion, the statistical spread of speeds around the average. Now, let's begin to connect that spread to mass. In a galaxy dominated by a massive dark halo, Those clusters should be whipping around fast, held in by a gravitational well far deeper than the visible stars alone can dig. Higher dispersion means more total mass. Low dispersion means a shallower well. It is the same logic used for decades with rotation curves of spiral planets of stars, just adapted to a fragile, ultra-diffuse system. Expectation versus reality again. The team found that DF2's globular clusters were not racing. The dispersion was very low, only a few kilometers per second, entirely consistent with what the gravity from the observed stars and gas could provide. No extra pull was required, no hidden reservoir of dark matter was demanded by the equations. When they translated that dispersion into a total mass, the answer hugged the stellar mass estimate. The galaxy's overall mass came out only slightly above the mass in normal matter alone. Within the uncertainties, there was little or no room for a massive, dark halo. By the end of tonight, you're going to understand why that single conclusion sent a shockwave through every model of galaxy formation. But uncertainties matter. DF2's case rests on a small sample of clusters, each velocity measurement carrying its own error bars, all interpreted under the assumption that the system is in equilibrium and not being torn apart by some external gravitational wind. Change those assumptions, and the inferred dark matter content can shift dramatically. No one predicts a clean, simple answer from a galaxy this strange. That is why DF2 didn't just look odd. It became a new boundary in the fight over what dark matter really is, and what happens if galaxies can live without it. So when the first detailed measurements came in, DF2 didn't just bend the rulebook of galaxy formation. It walked up to it, flipped it over, and asked whether anyone had actually read it. By the end of tonight, you're going to understand why this one faint smear of light in deep space sent shockwaves through both sides of a decades-long debate. Because on paper, DF2 should have been a dark matter fortress. Given its size and luminosity, standard scaling relations said it ought to contain perhaps a few hundred times more dark matter than stars. Ultra-diffuse galaxies are usually swimming in invisible mass. Their stars are spread out, their surface brightness is low, and the only way they stay bound in the violent gravitational wind of the cosmic web is by sitting inside enormous, dark halos. That's the expectation. Now, the reality. When scientists traced the tiny motions of compact star clusters orbiting inside DF2, the speeds came back. Small, almost boringly small. The inferred total mass of the system was only a little higher than the mass of the stars themselves. Not hundreds of times higher, maybe a factor of 2 within the uncertainties. In other words, the measurements suggested almost no dark matter at all. For standard dark matter cosmology, that is awkward. The whole picture of structure formation in the solar neighborhood and beyond says dark halos form first, then gas falls in, then stars and planets appear. Halos are supposed to be ubiquitous and to dominate the mass budget, especially in fragile diffuse systems like DF2. You can strip gas, you can strip stars, but peeling away almost an entire halo without shredding the galaxy into tidal debris pushes the physics to its limits. Now comes the twist. DF2 is not kind to the main alternative either. In modified gravity, theories like MOND, low accelerations trigger extra effective gravity. Dwarf galaxies and ultra-diffuse galaxies should look superbound, with stars moving faster than Newton's law with visible matter alone would allow. Yet DF2's internal motions looked almost perfectly Newtonian. No dark matter signal, no MOND boost, just a quiet, nearly textbook gravitational system where every observed star seemed to carry exactly the weight its light implied. No one expects both camps to be uncomfortable at the same time. No one predicts a galaxy that undermines the need for dark matter in one breath and undercuts modified gravity in the next. The reaction was immediate. Some scientists were electrified. If this result held, it could prove that dark matter is a real, separable component, not just a tweak to gravity, because here was a galaxy with the same gravity but none of the invisible ingredient. Others were skeptical. Were the distances off? Were the star clusters special? Had the mission to weigh this galaxy crossed an unseen observational boundary? Within months, papers appeared arguing tidal interactions, exotic formation histories, and plain measurement error. Some said DF2 might be a one-off fluke, a statistical outlier that the universe occasionally throws into the mix. Now, let's begin to raise the stakes, because just as the community started to treat DF2 as a possible mismeasurement, a second galaxy quietly stepped forward with the same bizarre property, and that's where the rulebook really begins to burn. DF2 was weird. DF4 made it a crisis. Just a year after the DF2 announcement, astronomers turned their telescopes back to the same region of space, the NGC 1052 group, about 65 million light-years beyond our solar system. There, in the glow of that same massive elliptical galaxy, they discovered a near twin. Another ultra-diffuse smear of light, so ghostly that its stars are spread over a Milky Way-sized footprint, but with only a tiny fraction of the stars. The name was NGC 1052 DF4. The resemblance to DF2 was not subtle. The original plan is simple. Find faint, extended galaxies in deep images, then use follow-up spectroscopy to weigh them through the motions of their star clusters. No one expects lightning to strike twice in the same small group of galaxies. No one predicts that the second target will look dynamically just as bizarre as the first. Yet that is exactly what the spectra said. DF4, like DF2, hosts a handful of bright, compact, globular clusters orbiting in its diffuse halo. By measuring how the absorption lines in those clusters are Doppler shifted, scientists could infer their velocities along the line of sight. In a normal galaxy, with a standard dark matter halo, those velocities should be spread out, showing a healthy velocity dispersion that betrays the hidden mass. In DF4, the spread was tiny. The clusters moved so slowly relative to one another that their motions could be explained almost entirely by the visible stars. Prediction versus observation again. The standard model says galaxies live inside halos of dark matter that outweigh their stars by a factor of 5, 10, or more. DF2 already looked like an exception. DF4, with an independently measured low-velocity dispersion, made that exception much harder to dismiss as a fluke or a statistical mirage. Two ultra-diffuse galaxies, same group, same ghostly morphology, same hint of almost no dark matter. The odds that both are just measurement errors drop sharply when the anomalies line up this cleanly. By the end of tonight, you're going to understand why that repetition is what really set theorists on edge. Suddenly, the focus shifted from the galaxies themselves to their neighborhood. If DF2 and DF4 both live in the gravitational field of the massive galaxy NGC 1052, perhaps the environment is not just background scenery. Perhaps it is the main actor. Powerful tidal forces, repeated close passages, and interactions with the group potential could, in principle, strip away the loosely bound dark matter halo while leaving a fragile stellar core behind. That idea turns DF2 and DF4 from isolated curiosities into signposts of a process. Tonight, we're going to follow that thread, because once there are two, the conversation changes from patching DF2 with ad hoc excuses to asking whether there is an entire class of dark matter-poor satellites forming along the turbulent boundary of galaxy groups, and what that means for the mission of dark matter itself. But there's a catch hiding in plain sight. All of this drama about galaxies with no dark matter rests on a single, deceptively simple question. How far away are they, really? Because in extragalactic astronomy, distance is destiny. A galaxy's inferred size, luminosity, and mass all scale with how far it is. Double the distance and its physical size doubles. Its total light jumps by a factor of 4, and the mass you infer from that light rises with it. Bring DF2 and DF4 closer, and they shrink on every axis. Smaller, dimmer, less massive. Suddenly, their star clusters are much easier to bind with their visible stars alone, with no need for exotic invisible halos. The original claim that DF2 and DF4 live about 65 million light-years away came from two main clues. First, scientists used a technique called surface brightness fluctuations. In a galaxy that far, individual stars blur together, and the tiny pixel-to-pixel variations in brightness tell you how distant the whole system must be. Second, DF2 and DF4 sit on the sky right next to the massive galaxy NGC 1052. The assumption was straightforward. They belong to its group, at roughly the same distance, drifting along the same cosmic boundary between galaxies. No one expects distance to be the villain, but critics quickly pointed at that single number. What if DF2 and DF4 are not loyal satellites of NGC 1052, but foreground interlopers? If they sit, say, 40 million light-years away instead of 65, their physical sizes shrink by almost 40%, their luminosities drop, and the masses of their star clusters come down. The same measured velocities would then require far less gravity to keep those clusters bound. The galaxies would stop looking like dark matter-free anomalies and start looking like perfectly ordinary, low-mass systems. That challenge triggered a new mission of measurement. Independent teams went back with fresh data, including ultra-deep Hubble imaging, and used a different distance indicator, the tip of the red giant branch. Old, low-mass stars climb a well-understood brightness ladder before they suddenly cut off. That cut-off can act like a standard candle. By the end of tonight, you're going to understand why that matters. Those red giant measurements tended to support the original, larger distance within their uncertainties, though not every analysis agreed on the exact number. Pattern interrupt. This isn't just a technical argument over a few million light-years. In this regime, a 10–20% change in distance can flip the narrative. The same galaxy can move from needs no dark matter at all to fits the standard dark matter halo model just fine. No one predicts that such a modest tweak on the cosmic ruler could decide whether an entire theory of invisible mass survives contact with observation. Now, let's begin to follow the consequences of both possibilities, because what DF2 and DF4 mean for dark matter depends entirely on which distance story wins. Now, let's begin to ask a less glamorous but absolutely essential question. Could DF2 and DF4 only look strange because the measurements are fragile? In other words, are these galaxies really breaking the dark matter rulebook, or are we just pushing our instruments and statistics right to the edge of what they can handle? The first red flag is small number statistics. To weigh DF2 and DF4, scientists don't have thousands of stars mapped in exquisite detail. They have velocities for only a handful of bright, globular clusters orbiting each galaxy. Designed for sweeping surveys of the solar system's planets, space telescopes suddenly find themselves judging an entire invisible mass budget from maybe 7 to 10 tracers. No one expects that to be easy. With so few data points, random chance matters. A couple of clusters moving unusually slowly can drag the estimated velocity dispersion down. A couple moving fast can push it up. The inferred mass scales with that dispersion, so a tiny change in the spread of speeds becomes a huge change in how much dark matter is allowed. By the end of tonight, you're going to understand why a difference of just a few kilometers per second can flip a galaxy from no dark matter to perfectly ordinary halo. There is another catch. The standard mass estimating formulas assume the system is in dynamical equilibrium, a quiet balance between gravity and motion. But DF2 and DF4 live near a massive neighbour, NGC 1052, in a crowded region of space. If they were recently tugged, stretched, or shocked by tidal forces, the globular clusters might not be settled. Some might not even be gravitationally bound. Include an unbound cluster that is flying away, and the dispersion spikes high. Exclude it, and the galaxy suddenly looks feather-light. That is exactly where the debates begin. Alternative analyses take the same raw velocity measurements and refit them with different statistical assumptions, different priors on the dispersion, different treatments of measurement error, different rules for what counts as an outlier. Some reanalyses conclude that higher dispersions are still consistent with the data, which restores a healthy dark matter halo. Others argue the low dispersion remains robust. The boundary between these conclusions can be razor thin. Before we get started on exotic new physics, it helps to see how subjective choices creep in. Which clusters do you include when one has a suspiciously large uncertainty? Do you weight noisy data heavily or gently? When a single point sits far from the rest, is that a real physical outlier, a misidentified object, or a glitch in the spectrograph? Change those decisions and the same galaxy can be needs no dark matter at all or perfectly compatible with LCDM. So yes, the measurements are messy, but even if every velocity were perfect, another question looms just beyond the current boundary of the argument. Is there any realistic process in this universe that could strip almost all the dark matter from a galaxy, while leaving its fragile stars behind? There is, and it starts with a kind of cosmic peeling. Now, let's begin with something familiar. The moon pulls on Earth, but it doesn't pull every part of Earth equally. The side facing the moon feels a slightly stronger gravitational tug than the far side. That tiny difference stretches our oceans, raising tides. Those are tidal forces, gentle on a planet. But when galaxies get involved, the same physics turns brutal. Picture a small, fragile galaxy drifting through space on a long, looping orbit around a massive host. Its stars sit deep in the center, like the bright core of a peach. Its dark matter halo is the fuzzy skin and flesh around it, extended, diffuse, and only weakly bound. Every close pass by the giant galaxy is like a gravitational bite. The near side of the satellite feels a stronger pull, the far side a weaker one, and the outer dark matter begins to unbind. Tonight, we're going to follow that orbit. On the first pass, not much happens. A little stretching. A few particles of dark matter flung outward beyond the system's gravitational boundary. On the second and third passes, the effect compounds. More of the halo is stripped, trailing behind like a faint invisible wind of particles. The dense stellar core, where gravity is strongest, hangs on. The dark matter in the outskirts does not. Simulations have run this mission over and over. Change the orbit. Change the mass ratio. Change the internal structure of the satellite. Again and again, scientists discovered the same pattern. Repeated tidal encounters can shear away a huge fraction of a galaxy's dark matter, while leaving a recognizable stellar system behind. Some models end with satellites that have lost 80, 90, even 95% of their original dark halos. By the end of tonight, you're going to understand why that number matters. Galaxies are usually dominated by dark matter, with 5 to 10 times more dark mass than normal matter. If tides can erase most of that, they can manufacture a galaxy that looks, at first glance, almost dark matter-free. Not because dark matter never existed there, but because it has been peeled off and dispersed into the larger system. Now, connect that to the real sky. NGC 1052 DF2 and NGC 1052 DF4 both live in the gravitational neighborhood of a massive elliptical galaxy called NGC 1052. They are not isolated islands drifting alone through the cosmic ocean. They are lightweight companions sitting deep in the potential well of a heavyweight, exactly where tidal forces should be strongest. No one expects a small satellite to pass repeatedly near such a behemoth and emerge unchanged. No one predicts its halo will stay pristine. The tidal stripping story says DF2 and DF4 are survivors of violence, the bare stellar cores left after their halos were shredded. But here is the uncomfortable question that waits just beyond that elegant explanation. Can tides really remove almost all the dark matter, while leaving such diffuse, ghostly stars still arranged in a calm-looking galaxy? And if this violence happened, where are the visible scars? If a galaxy has been mauled by gravity, the universe usually leaves fingerprints, long, ghostly fingerprints. Tonight, we're going to read those scars. When two galaxies pass close, their gravity doesn't just pull, it stretches. Stars, gas, and even dark matter feel a changing gravitational field across the system, stronger on one side than the other. That difference acts like a cosmic tide. It can draw out enormous, faint ribbons of material called tidal tails and streams, arcs that can span hundreds of thousands of light years, barely brighter than the glow of the night sky itself. These are not theoretical decorations. Deep images of the space around big galaxies like Andromeda or around dense galaxy clusters reveal spectacular loops, plumes, and shells. Each one is a frozen record of a past encounter, the visible memory of a smaller system being torn apart. The mission for astronomers studying DF2 and DF4 is simple in concept and brutal in execution. Look for similar scars in the NGC 1052 group. If DF2 and DF4 really had their dark halos stripped away, expectation is clear. You would predict debris, stellar streams peeling away from them, twisted arcs linking them back to a larger companion, or diffuse fans of stars scattered through the group. The contrast pair is stark. A quiet, untouched galaxy should look smooth and symmetric in deep exposures. A survivor of a gravitational assault should look subtly or dramatically disturbed. To test this, scientists push imaging to the edge of what current telescopes can do. Long exposures on big instruments, careful subtraction of foreground stars, and sophisticated processing reveal features millions of times fainter than the planets in the solar system's night sky. Around NGC 1052, they have discovered low surface brightness structures, asymmetries in the light, wispy extensions, nearby stellar streams that snake through the group environment like frozen rivers. Some of these features seem tantalizingly close to DF2 and DF4. A faint stream here, a lopsided glow there. No one expects a neon sign pointing to a single violent event, but any coherent arc that passes near these galaxies becomes a candidate clue. Are these the remnants of the encounter that stripped their dark matter, or unrelated scars from other past mergers in the same crowded region of space? Here is where the mystery deepens. The images do not show a dramatic, textbook pair of tidal tails clearly anchored to DF2 or DF4. That absence weakens the simplest version of the stripping story, but it does not kill it. Tidal debris fades. Over a few billion years, streams disperse, phase mix, and sink into the background glow. By the end of tonight, you're going to understand why a clean sky does not guarantee a quiet history. Across galaxy groups and clusters, deep surveys find that tidal features are everywhere. Loops around ellipticals, shell systems around lenticulars, sprawling streams around spirals. No one predicts such scars would be rare. Absolutely no one anticipates pristine isolation. Interactions are common. The boundary between a normal galaxy and a shredded remnant is porous, and that makes a dark matter-poor survivor like DF2 or DF4 not just possible, but almost inevitable. Now, let's begin to ask a harder question. Even if tides shaped these galaxies, do their internal motions really add up to zero dark matter, or is something deeper hiding in the data? If tides can sculpt a galaxy like DF2, there's an even stranger possibility waiting in the wings, galaxies that are born with almost no dark matter at all. Not stripped, not damaged, just assembled from the wrong ingredients from the very beginning. To see how that can happen, follow two massive disk galaxies as they plunge toward each other in deep space. Their dark matter halos interpenetrate and keep going, but their visible disks of gas and stars slam together, twist and tear. Enormous tidal tails arc outward, tens of thousands of light years long, like luminous ribbons flung beyond the main system. In those tails, gravity doesn't just switch off, it reorganizes. Clumps of gas and stars in the tails can slow down relative to the flow, pile up, and become self-gravitating. Over tens of millions of years, those clumps collapse, condense, and ignite new waves of star formation. The result is astonishing, a brand new small galaxy hanging off the parent like a glowing bead on a torn thread. Astronomers call these objects tidal dwarf galaxies. Here's the crucial twist. Those tidal tails are made from the baryonic outskirts of the original disks, gas, dust, and stars that lived in the thin, rotating planes of the parent galaxies. The dark matter, in contrast, sits in a much larger, more diffuse halo that doesn't get dragged into narrow tails as easily. So, when a tidal dwarf condenses out of a tail, it forms almost entirely from ordinary matter, with little access to the surrounding dark reservoir. From birth, it is predicted to be dark matter poor. This isn't just a theoretical curiosity. In systems like the antennae galaxies, where two spirals are colliding about 60 million light-years away, telescopes have discovered bright, compact knots along the sweeping tidal arms. They host young, massive stars glowing in ultraviolet and H-alpha, with gas clouds that rotate as tiny, coherent systems. They look like nascent galaxies lit up by furious star formation, still tethered to their parent encounter by a faint tidal bridge. Now, put those side by side with DF2 and DF4. Tidal dwarfs are usually small, only a few thousand light-years across. DF2 and DF4 are larger, ultra-diffuse systems that rival the Milky Way's disk in radius, while holding only a whisper of its stellar mass. Tidal dwarfs are young and blue, blazing with recent star formation. DF2 and DF4 are old and red, their stars formed long ago. Tidal dwarfs are compact and clumpy. DF2 and DF4 are ghostly, with stars spread thinly across a vast area. So here comes the pattern interrupt. If DF2 doesn't look like a tidal dwarf now, could it be an evolved one? By the end of tonight, you're going to understand why some scientists have proposed multi-stage interactions. First, a violent encounter flings out baryonic material and builds a dark matter-poor seed. Later, additional passes stretch, puff up, and age that seed into the diffuse, quiescent remnant seen today. No one predicts that a single collision writes the whole story. Before we get started on those scenarios, there's a catch. To claim a galaxy has no dark matter, its internal motions must be measured with exquisite care. The next step in this mission is to ask whether the data behind DF2 and DF4 are really as clean as they look, or whether the solar system-sized uncertainties in distance and velocity are quietly rewriting the conclusion. Those uncertainties are the observational side of the mission. But there's a second front where the mystery is attacked with pure theory and raw computing power. Tonight, we're going to dive into simulations that try to build a galaxy, like DF2 or DF4, from the ground up and ask, can gravity alone carve out islands of stars with almost no dark matter? In large cosmological simulations, scientists start with a smooth, expanding sea of dark matter and gas and let the laws of physics run. Gravity pulls matter into clumps. Those clumps merge into halos, and within those halos, stars ignite. The result is a synthetic universe, a digital space full of galaxy groups, satellites, and tidal debris. Crucially, the code tracks dark matter and baryons separately, so every interaction, every close passage, every tidal encounter leaves a trace in both the invisible halo and the visible stellar system. Now, let's begin to zoom in. In so-called zoom-in simulations, a single galaxy group is re-simulated at much higher resolution. The host, its satellites, and the surrounding cosmic web are followed in exquisite detail, almost down to individual giant molecular clouds where stars form. When a small satellite plunges through the deep potential well of its host, the model records exactly how much dark matter is peeled away, how its stellar body is stretched, and whether the remnant survives as a recognizable galaxy. Several teams have gone hunting in these digital universes for satellites that have been stripped to the bone. They scan the catalogues for objects whose stars are still bound, whose sizes resemble ultra-diffuse galaxies, but whose dark matter halos have been shredded by repeated orbits through a massive group. In those runs, no one expects to find many systems that are truly dark matter-free. But some simulations do reveal survivors with dark matter fractions slashed by factors of 10 or more compared to typical dwarfs. In a few striking cases, the simulated remnants end up with stellar masses, sizes, and internal motions that look eerily similar to DF2 and DF4. The prediction versus observation tension softens. If a satellite is dragged through a dense region near a massive central galaxy, the outer halo is stripped first, then more, until the stars are left riding in a shallow, nearly naked potential. For a brief window in cosmic time, the system behaves like a galaxy, where the visible mass tells almost the whole gravitational story. But there are serious limitations. Resolution is finite. Each dark matter particle can represent thousands of solar masses, so the fine structure of the halo and the exact boundary where stars detach are blurred. The baryonic physics is handled with subgrid recipes for star formation, feedback, and the multiphase interstellar medium tuned to match whole populations of galaxies, not one peculiar ultra-diffuse outlier. And even when a DF2-like object appears, its orbit, age, and environment often fail to match the precise conditions discovered around the real galaxies. By the end of tonight, you're going to understand that simulations are not oracles, they are laboratories. They show that dark matter-poor remnants are dynamically plausible, but they are rare, transient, and usually caught in the act of being torn apart. That raises a sharp question for the next section. If these fragile systems should flicker in and out of existence, why do observations report several of them in the same group, right now, within the same cosmic neighborhood? So when several DF2-like galaxies show up in the same group at the same cosmic moment, it sounds less like a fluke and more like a pattern. And when there's a pattern, the mission shifts. Tonight, we're going to treat these galaxies not as mistakes, but as messages about how the universe really builds and breaks its systems. At first glance, a galaxy with almost no dark matter looks like a direct attack on dark matter itself. If dark matter is the invisible scaffolding holding galaxies together, then finding a galaxy that seems to ignore that rule feels catastrophic. But expectation is one thing. Cosmic reality is another. In modern cosmology, the dark sector and normal or baryonic matter are not welded together. They can be separated, pushed apart, and rearranged by the violent weather of space. Simulations show this clearly. Feedback from exploding stars can blow gas out of small halos. Ram pressure stripping, as a galaxy plunges through a thicker intergalactic medium, can peel away gas while leaving the dark halo behind. Tidal forces from nearby massive planets of stars, entire galaxies acting like gravitational flybys, can do the opposite, shredding the dark halo and leaving a luminous remnant. No one predicts these processes will always line up neatly. So finding systems that are mostly dark matter or mostly baryons is not a contradiction, it is a calibration point. DF2-like objects, if their low dark matter content holds up, become laboratories. They let scientists watch how stars and gas orbit when they are not buried deep inside a massive halo. The stellar velocity dispersion, the thickness of the disk or spheroid, the way star clusters survive or dissolve over billions of years, all of that becomes a direct probe of gravity with minimal dark background. By the end of tonight, you're going to understand why that is incredibly valuable. It pins down how star formation and stellar feedback operate when the usual dark cushion is missing. These odd galaxies also push on a quieter but crucial part of cosmology, the link between halo mass and stellar mass. Most models assume a relatively tight stellar-to-halo mass relation, with some scatter. DF2, DF4, and their cousins live out in the tails of that distribution. They tell scientists how wide those tails can really be. If a few % of halos can end up nearly starless, or a few luminous galaxies can end up nearly haloless, the whole population of galaxies must be retuned in simulations to match what is actually discovered. So dark matter-poor galaxies do not automatically kill dark matter. They stretch it. They force the theory to survive at the extremes. But there is another framework on the table, one that tries to remove dark matter entirely by changing gravity itself. And here is the real twist. Could these galaxies, instead of being deadly for dark matter, become fatal for its main competitor? Modified gravity theories? So if dark matter-poor galaxies stretch the standard picture, what do they do to the rival theory that tries to erase dark matter completely? Tonight, we're going to dive into the framework that says the universe never needed invisible mass in the first place. It just needed different gravity. Now, let's begin. MOND, or modified Newtonian dynamics, starts from a bold move. Instead of adding a hidden halo of particles around galaxies, it changes the law of motion itself, when accelerations become extremely small, far below anything experienced in the solar system. In that low acceleration regime, gravity does not fade as quickly as Newton predicted, so stars in the outer parts of galaxies can orbit faster without invoking dark matter. Same visible mass, new rulebook. In this picture, the key quantity is not just how much mass a galaxy has, but how spread out that mass is. Low surface brightness means the same total mass smeared over a much larger area, which means weaker internal gravitational accelerations. According to Mond, those ultra-weak accelerations are exactly where the modified law should light up. These galaxies should be the prime mission targets where the new gravity dominates, where rotation curves refuse to fall, and orbital speeds stay high long after Newtonian gravity says they should drop. That is the expectation. But then galaxies like NGC 1052, DF2 and DF4 show up, and the reality looks very different. These systems are incredibly diffuse, ghostly smears of stars drifting through space with extremely low surface brightness. In Mond language, they live deep in the low acceleration regime, far beyond the comfortable boundary where Newton's law has been thoroughly tested. Yet, when scientists measure the motions of their star clusters, the inferred gravity looks almost perfectly Newtonian. No extra boost, no hidden Mond effect, and crucially, no need for either dark matter or modified gravity to explain the observed speeds. Prediction versus observation could not be more stark. Galaxies that should be Mond's showcase laboratories instead look like quiet demonstrations of old-school Newton. Supporters of modified gravity have not given up. Some argue that DF2 and DF4 are feeling the gravitational pull of nearby massive galaxies, an external field that can suppress Mond effects and push them back toward Newtonian behavior. Others suggest these galaxies might not be in equilibrium at all. Perhaps they are still settling after a violent encounter, so their internal motions do not yet trace a clean gravitational potential. The debate becomes a mission of finding just the right environment, just the right history to keep Mond alive. But here is the emerging tension. If more and more galaxies are discovered in extreme low acceleration regimes with ultra-diffuse light profiles, and their internal motions still follow Newton's law with little or no dark matter, modified gravity faces an increasingly steep uphill battle. How many exceptions can a theory absorb before the exceptions become the rule? And what if the next surprise is even worse for Mond, yet strangely helpful for dark matter itself? So if DF2 and DF4 don't immediately kill modified gravity, what do? They open a door. Because once you have even one galaxy that seems to live at the edge of what any theory can handle, scientists don't shrug and move on. They start hunting for cousins. Now, let's begin. DF2 and DF4 are not alone. Over the last decade, observers have uncovered a whole menagerie of ultra-diffuse galaxies in different corners of space whose motions hint at lower than expected dark matter content. Some sit near massive hosts, some float in small groups, and a few appear in quieter regions, but they share a theme. For their size and dim, extended light, their internal speeds look strangely modest. In galaxy clusters like Coma, this becomes especially dramatic. The original expectation is simple. Drop fragile, puffed-up galaxies into a deep cluster potential, and they should need enormous dark matter halos just to survive the gravitational tides. The reality? Surveys with wide-field cameras and deep spectroscopy have discovered ultra-diffuse galaxies spanning the full spectrum. Some are extremely dark matter-dominated, with stars moving so fast that only a huge, invisible halo can hold them in. Others, with nearly identical light profiles, have velocity dispersions so low that they seem almost weightless by comparison. That contrast is a pattern interrupt. Same kind of galaxy, same cluster environment, completely different dark matter fractions. It forces a question. Are these galaxies born this way, or did the cluster environment sculpt them, stripping halos in some cases while leaving others nearly intact? Complicating things further, some early headlines about dark matter-free systems have not survived contact with better data. A few galaxies first reported as having almost no dark matter turned out, after improved distance measurements, to be closer and less massive than assumed. Others gained or lost apparent dark matter when more precise velocities for their star clusters were obtained. Prediction versus observation plays out in real time. Refine the distance, the inferred mass changes. Refine the motion, the dark matter fraction shifts. Before we get started on grand conclusions, that evolution matters. It shows that this field lives on the edge of current instruments, where small errors in distance, in velocity, in membership of star clusters can swing a galaxy from normal to impossible and back again. Tonight, we're going to lean into that uncertainty, because it's exactly why the search has gone systematic. Astronomers are no longer waiting for accidental oddballs. Wide imaging surveys flag ghostly. Extended galaxies, follow-up spectroscopy measures the motions of stars and globular clusters. Simulations predict which environments should produce DF2-like systems. By the end of tonight, you're going to understand that a single weird galaxy can be a fluke. A population spread across groups and clusters with shared traits and shared tensions is something else. It's a clue that the dark matter mission is about to cross a new boundary. And the next section is where those clues start to converge. Those DF2-like galaxies feel like an ambush. They look wrong for dark matter. But to really feel how strange they are, you have to meet their mirror image, galaxies that seem to be almost nothing but dark matter. Now, let's begin with some of the faintest companions of the Milky Way, ultra-faint dwarf galaxies. On a telescope image, they barely register. A few thousand, maybe a few tens of thousands of stars, scattered like a loose spray of pixels. And yet, when scientists measure how fast those stars move, something wild appears. The stars are racing around as if there were millions of solar masses holding them in. Expectation, dim galaxy, low mass, gentle motions. Reality, dim galaxy, enormous mass, frantic motions. No one expects a system that looks so fragile to be that heavy. Astronomers talk about this in terms of mass-to-light ratio. How much mass you need compared to how much starlight you see. The Sun has a ratio of about 1 in these units. Normal galaxies might be 10, 20, maybe 50. Some of these ultra-faint dwarfs clock in at hundreds, a few push toward 1,000. That's the opposite extreme of DF2-like galaxies. Instead of no dark matter, it's almost all dark matter with a sprinkling of stars. Here's the twist. These dark matter-dominated dwarfs actually fit comfortably inside the standard dark matter halo framework. In cold dark matter simulations, small halos form first, merge, and grow. Many of them never get enough gas to form a proper galaxy, or they have their gas stripped by the Milky Way's hot halo and solar wind-like outflows. What's left is a dense knot of dark matter with just enough stars to light up the potential well. Because they are so dominated by dark matter, these dwarfs become precision laboratories for the invisible. Their internal structure, the way density rises toward the center, the way velocity dispersion changes with radius, lets scientists test what kind of particle dark matter could be. If dark matter self-interacts, it can puff out the center. If it's warm rather than cold, it erases the tiniest halos and changes how many ultra-faints should exist. Every star in those galaxies is a tracer, like a tiny spacecraft mapping the gravitational field. Before we get started on galaxies with no dark matter, notice the pattern interrupt here. Same universe, same cosmic web, but the relationship between stars and dark matter can flip, depending on formation history and environment, tidal forces, early feedback, proximity to larger planets of the galactic system. All of that can push matter around in very different ways. So, if some galaxies are almost pure dark matter and others appear to be almost pure stars, what does that really say about how galaxies and halos connect? The next section pushes that question to its breaking point. So if some galaxies are almost pure dark matter and others appear to be almost pure stars, what does that really say about how galaxies and halos connect? Now, let's begin. In the standard picture, every galaxy lives inside a dark matter halo, not just casually, but in a tight statistical partnership. Scientists call it the stellar-to-halo mass relation, and it acts like a cosmic conversion chart. For a given number of stars, there is a typical total halo mass that the universe seems to prefer. This relation doesn't come out of thin air. It's carved out by observations of millions of galaxies matched to giant simulations of structure forming in space from the Big Bang to now. Here's the expectation. Take a galaxy with a certain stellar mass. Plug that into the relation. You get a predicted halo mass, usually 5 to 10 times larger than the mass in stars. Do this across the whole cosmic population, and a narrow band appears. Most galaxies hug this curve with only modest scatter. Some are a bit more efficient at turning halo material into stars. Some are less efficient, but they still live in the same basic neighborhood on the plot. DF2-like systems blow that neighborhood apart. On the stellar-to-halo diagram, they don't just sit low, they plunge far below the band, with stars that seem to be floating in space with almost no dark matter halo at all. Prediction: a hefty, invisible halo enveloping the galaxy. Observation: stellar motions that can be explained almost entirely by the visible mass. No one expects a galaxy to land there. No one predicts a system that bright, that extended, with so little dark matter holding it together. That tension is exactly why these galaxies are so valuable. They are stress tests on the galaxy-halo connection. If a few outliers can exist, then the relation is not a rigid law. It's an emergent trend with rare but extreme exceptions. By the end of tonight, you're going to understand that those exceptions are clues. They point to physical processes that can decouple star formation from halo growth, especially near massive neighbors where tidal forces, mergers, and the gravitational wind of a crowded environment can strip halos, rearrange orbits, and leave behind dark matter-poor remnants. In response, theorists have upgraded their simulations. New models don't just let halos grow in isolation. They drop galaxies into dense clusters, slam them through repeated encounters, and let satellite systems be torn apart. When environmental stripping, mergers, and violent feedback are all turned on, a broader range of galaxy-halo combinations appears, including rare islands of stars with truncated halos. So these dark matter-poor galaxies are not just curiosities parked at the edge of the data, they are anchor points that force the entire mission to be recalibrated. They tell us the stellar-to-halo relation can bend, fracture, and evolve across cosmic time. And if the relation can break this badly, the next question is brutal. Are we misreading the halos or the gravity itself? So, if the halos can lie, maybe the culprit is not gravity at all, but the dark component itself. What if the invisible scaffolding of the cosmos is not a perfectly cold, perfectly collisionless background, but a medium with texture, friction, and pressure? Tonight, we're going to push the dark matter into the lab of imagination and ask how different physics might redraw the map. Before we get started, take the standard picture. Dark matter is supposed to glide through space like a ghost. It feels gravity and nothing else. No collisions, no drag, no scattering. That elegant assumption lets scientists run clean simulations of how halos grow, merge, and cradle galaxies across the expanding universe. But it is an assumption. Nature never signed a contract. Now, let's begin. There is a family of models called self-interacting dark matter, SIDM for short. In these scenarios, dark matter particles can occasionally scatter off each other, the way molecules in a gas bounce around, trading energy and momentum. The cross-section can be tiny, far weaker than anything in the solar system's particle accelerators, but over billions of years and across galactic distances, those rare encounters can add up. In a standard cold, dark matter halo, the density shoots up toward the center, creating a steep cusp. SIDM changes that story. When particles scatter, they can conduct heat from the warmer outer halo into the cooler inner regions. The result is counterintuitive. Instead of packing more mass into the core, the inner dark matter can be pushed outward, flattening the profile into a broad core, where the density is almost constant. The inner galaxy becomes less dark matter dominated, even if the total halo mass hardly changes. This matters because the galaxies like NGC 1052 DF2 are judged by their inner dynamics. Astronomers look at the velocity dispersion of star clusters and planetary nebulae inside a few kiloparsecs and compare it to the visible mass. If SIDM has already evacuated the central dark matter and then tidal forces from a massive neighbor strip the puffed-up outer halo, the remnant could be extreme. A system whose stars in the region we can measure move as if almost no dark matter is present at all. No one expects a single tweak to fix every anomaly. No one predicts that one clever scattering cross-section will simultaneously explain ultra-diffuse galaxies, cluster cores, and DF2-like objects without creating new tensions somewhere else. And absolutely no one anticipates rewriting particle physics just to save a handful of controversial data points. By the end of tonight, you're going to understand why most researchers still reach first for standard cold, dark matter plus harsh environments. Simulations already show that tidal stripping and mergers can carve out galaxies that temporarily look dark matter poor, without invoking exotic new forces. The current DF2-like observations do not yet demand SIDM or any other radical mission redesign, but anomalies have a long history of ambushing our best theories. If even a few of these galaxies truly live on the edge of the expected dark-to-stellar ratio, they could be signposts toward new physics. Before announcing a boundary breach in the dark sector, though, the community needs something crucial: absolute confidence that the measurements are not lying. So the next step is brutal and technical. How do you tighten the observational screws until the galaxies themselves have nowhere left to hide? So the next step is brutal and technical. How do you tighten the observational screws until the galaxies themselves have nowhere left to hide? You do it the same way the edge of the solar system was redrawn, with sharper eyes, deeper spectra, and instruments that push far beyond what the original mission planners thought was possible. Right now, much of the case for galaxies like NGC 1052, DF2 and DF4 rests on a handful of tiny points of light. Hubble and the largest ground-based telescopes resolve individual stars and globular clusters in these ghostly systems, turning smudges into rich, detailed star fields. Designed to map nearby galaxies in broad strokes, they are now being pushed to isolate star clusters only a few parsecs across at tens of megaparsecs away. That resolution is what lets scientists even attempt to weigh these galaxies one tracer at a time. But with only a dozen or so tracers, velocity dispersion becomes a noisy statistic. One outlier cluster, one mismeasured line, and the inferred dark matter content swings wildly. The solution is simple in principle and brutal in practice: more spectra. Deeper spectroscopy on 8 to 10 meter class telescopes and soon on even larger mirrors will gather velocities for many more globular clusters, for planetary nebulae, and even for the integrated light of the diffuse stellar body. The more independent test particles you have orbiting in the gravitational field, the tighter you can pin down that invisible mass. Here is the pattern interrupt. This is not just an optical story. Radio telescopes can map neutral hydrogen gas extending far beyond the visible stars, tracing rotation curves out where dark matter usually dominates. If DF2 or DF4 host extended HI disks, their outer gas velocities will provide a completely independent check on whether the gravity field fades with the light or keeps rising the way dark matter-dominated galaxies do. In some cases, the absence of gas is itself a clue to a violent tidal history. Tonight, we're going to mentally fast-forward a decade. By the end of tonight, you're going to understand why upcoming facilities may decide this debate. The James Webb Space Telescope is already resolving fainter stars in crowded fields, pushing distance estimates and stellar populations to new precision. Extremely large telescopes on the ground with mirrors 25 to 40 meters across will take that further, delivering razor-sharp images and high-resolution spectra of galaxies that are now just whispers in the noise. No one expects all current dark matter-free candidates to survive this onslaught unchanged. No one predicts that every claim will evaporate, either. The boundary between normal, dark halos and true anomalies will be redrawn as better data arrive, just as the boundary of the heliosphere was moved when the solar wind was finally measured in situ. The key point is that this is a live, evolving story. Now, let's begin to ask, when the data harden, what would each possible outcome really mean for dark matter itself? When you claim a galaxy has almost no dark matter, you're really making a statement about gravity itself, about how much mass must be there, hidden or not. So the next question is brutal and simple. Can that mass be weighed without trusting the motions of stars at all? That is where light starts to curve. By the end of tonight, you're going to understand why one of the most powerful tools in modern cosmology is not a new kind of telescope, but a natural optical trick in space. Gravitational lensing, massive objects bend the path of light from more distant galaxies. The more mass along the line of sight, the more the light path is deflected, even if most of that mass is invisible. It turns the universe into a giant, slightly warped lens. In its most dramatic form, this lensing is impossible to miss. Strong lensing takes a single background galaxy and stretches it into arcs, rings, or multiple images. A galaxy cluster with a huge dark matter halo can act like a cosmic magnifying glass, distorting and multiplying galaxies far beyond it. The boundary between normal images and these surreal curved apparitions is set by the total mass, not by how bright the cluster looks. But most of the time, the effect is subtle. No one expects perfect Einstein rings in random patches of sky. Instead, weak lensing shows up as tiny, statistical distortions in the shapes of millions of background galaxies. On their own, those galaxies are messy. In aggregate, a preferred direction appears, revealing where the foreground mass is concentrated. From this, scientists can map dark matter directly, without caring how any particular galaxy rotates. Now, let's begin to connect this back to a system like NGC 1052 DF2. DF2 itself is far too low mass to create strong lensing features. No rings, no giant arcs, no multiple images of background planets or galaxies. But DF2 does not float alone in a cosmic void. It lives in a group environment embedded in a larger halo whose lensing signature, in principle, can be measured. If the host group's weak lensing signal is well understood, it becomes an independent check on how much dark matter should be available to feed, strip, or sculpt galaxies like DF2. This is not just theory. In clusters such as the Bullet cluster, strong and weak lensing have already delivered some of the clearest evidence that dark matter is real. The hot gas, glowing in X-rays, is slowed and displaced by a collision, while the lensing map shows most of the mass racing ahead with the galaxies. Prediction said mass should track the ordinary matter. Observation said the mass and the gravitational potential are somewhere else. No one predicts that DF2 alone will overturn that entire framework. Lensing nails down that there is a gravitational component beyond normal matter on large scales. That makes galaxies that appear dark matter-free not a reason to abandon dark matter, but a sharper puzzle inside a theory that otherwise works astonishingly well. The mission now is to explain how such outliers can exist without breaking the larger cosmic lens. Before we get started on those explanations, there is one more angle. What if the problem is not the galaxies, but gravity itself? Or, what if the problem is not gravity at all, but distance? When a galaxy looks impossibly light, one of the first suspects is not exotic physics, but a very human issue. How far away it really is. Now, let's begin. Astronomers do not get a cosmic tape measure. They build something more fragile and more powerful, a distance ladder. The first rung is geometric. Nearby stars shift their apparent position against the background as Earth moves around the Sun. That tiny wobble is parallax. From it, scientists can measure distances to a few thousand light-years with almost pure geometry. Beyond that, geometry runs out. So the next rung uses standard candles, objects whose true brightness is known. Cepheid variable stars pulse with a period that tracks their intrinsic luminosity. Measure the period, compare true brightness to how faint they appear, and the distance drops out. Type Ia supernovae do something similar on a grander scale, exploding with nearly standard peak luminosity that can be seen across hundreds of millions of light-years. Farther still, the ladder leans on secondary indicators. One of the most important for nearby galaxies is called surface brightness fluctuations. In a smooth galaxy image, the graininess from unresolved stars gets weaker with distance. Calibrate that graininess using galaxies with known distances, and suddenly even diffuse systems tens of millions of light-years away have estimated positions in space. But every rung carries its own assumptions, its own calibration errors, its own hidden biases. A tiny shift in the Cepheid period luminosity relation, a subtle population difference in red giant stars, or a miscalibrated fluctuation scale can propagate upward. By the time the ladder reaches a faint, ghostly galaxy like DF2, the uncertainty can be enormous. Here is where the illusion becomes dramatic. Imagine a galaxy whose distance is overestimated by 30%. That does not sound catastrophic, but the inferred size scales directly with distance, so the galaxy appears 1.3 times larger. The luminosity scales with distance squared, so it looks roughly 1.7 times more luminous. Feed that into mass estimates, and both the visible mass and the dynamical inferences can swing, making the same system appear nearly twice as big and about 4 times as bright. A modest distance error turns into a radical claim about missing dark matter. No one expects a single number on a plot to carry that much leverage. Yet for DF2, that leverage became the whole story. Some reanalyses argued that DF2 was not about 20 megaparsecs away, but closer to 13. At that nearer distance, its stars would be less luminous, its size more modest, and its motions entirely compatible with a normal dark matter halo. The galaxy would still be odd, but not revolutionary. To test this, Hubble was pushed to its limits. The mission: resolve individual red giant stars in DF2. If the telescope could see the tip of the red giant branch, that feature would act as another standard candle. The result? The best measurements pointed back to a larger distance close to the original value. By the end of tonight, you're going to understand why that single conclusion kept the dark matter-free interpretation alive. The balance of evidence today favours DF2 being as far and as weird as first reported. No one predicts a galaxy where the visible mass alone explains the internal motions, yet that is what the data still suggest. But this episode exposes a deeper lesson. When claims rest on barely resolved stars, tiny fluctuations in surface brightness, and ladder rungs stacked across millions of light years, they are powerful and fragile. Absolutely no one anticipates how much our picture of dark matter can hinge on a few photons from the edge of space. And that fragility raises the next question. If the distances are right, how could a galaxy lose nearly all of its invisible halo without tearing itself apart? If a galaxy can lose most of its dark halo without flying apart, there's only one way that makes sense. Its stars have to be moving through a stable, gravitational landscape. But what if that landscape is changing right now? What if we're taking a snapshot in the middle of a cosmic traffic accident and treating it like a posed portrait? Standard mass estimates quietly assume dynamical equilibrium. The idea is simple and powerful. Over billions of years, stars, globular clusters, and gas clouds orbit within a galaxy's gravitational potential, trading kinetic energy for potential energy until their collective motions settle into a steady, statistical balance. Measure how fast those tracers move. Combine that with their typical distances from the center, and you can infer how deep the potential well is. Deeper well, more mass. Shallow well, less mass. That logic works beautifully for big, relaxed systems. Spiral galaxies with smooth rotation curves, elliptical galaxies whose random stellar motions have been stable for ages. But galaxies are not isolated planets drifting peacefully through space. They live in a crowded cosmic web, pulled, stretched, and harassed by neighbours. When a recent tidal interaction rips through, the whole assumption of equilibrium can fail in spectacular ways. Imagine a small, ultra-diffuse galaxy brushing past a massive companion. The encounter can strip away dark matter from the outskirts, fling stars onto elongated orbits, and carve tidal tails that reach far beyond the visible core. In simulations right after such a stripping event, the remaining tracers in the central region can look deceptively calm. Their velocity dispersion drops. Motions become anisotropic, mostly in one direction or confined to a thin plane. So simple, spherically symmetric models read them as cold. The boundary feels shallow even when the underlying potential is deeper and more complex. Tonight, we're going to lean into that possibility for DF2 and DF4. Could these galaxies be caught in a transient phase only tens or hundreds of millions of years after a violent encounter when the solar system-style balance astronomers expect has not yet been restored? By the end of tonight, you're going to understand why some scientists argue that what looks like a nearly dark matter-free system might just be an out-of-equilibrium survivor. There are telltale signatures, asymmetries in the light distribution, subtle tidal tails arcing toward a nearby massive galaxy. Velocity gradients across the face of the system, hinting at bulk flows rather than settled orbits. Simulations predict that these features should accompany the cold dispersions in the brief window after stripping. No one predicts a perfectly smooth, undisturbed remnant. Now, let's begin to tighten the net. If improved imaging fails to reveal strong tidal distortions, if more tracers still show improbably low dispersions from every angle, and if the motions line up with equilibrium models rather than chaotic flows, then one by one the escape hatches close. No one expects that outcome. Absolutely no one anticipates what it would mean, that some galaxies may truly be almost naked, their stars drifting through space with virtually no dark matter at all. If galaxies really can go almost naked, the next question hits hard. How do you even build a galaxy without its dark matter halo? By the end of tonight, you're going to understand why that sounds like saying you built a solar system with no central star, and yet there are still pathways within physics that could get you there. Now, let's begin. In standard cosmology, dark matter collapses first, forming invisible wells in space. Gas falls in, cools, forms stars, and a galaxy is born wrapped inside a massive halo. Take away that halo and the whole mission should fail. So if these objects are real, there are two main channels scientists focus on: galaxies that start life already baryon only, and galaxies that start normal and then get almost all their dark matter torn away. The first channel lives in the chaos of galaxy collisions. When two big galaxies interact, their gravity pulls out long, thin tidal tails of gas and stars. In those tails, clumps can collapse and ignite new stars. These are tidal dwarf galaxies. They form from material ripped out of regular galactic disks, not from pristine dark matter halos, so they should be almost pure baryons from the beginning. No one predicts them to be common, but in a violently interacting group, they can be manufactured again and again. The second channel is more brutal. Imagine a small dark matter-rich dwarf orbiting a massive central galaxy. Each close pass through the group potential strips away its outer halo. First the dark matter goes, then the loosely bound stars, until only a compact, dark matter-poor core remains. In simulations, extreme tides can peel off more than 90% of the dark mass, leaving a faint, puffed-up remnant, whose internal motions are set almost entirely by its visible stars. Then come the hybrid stories. A tidal dwarf born nearly halo-free might later sweep up star clusters and gas from the group environment, building a diffuse stellar system without ever acquiring much dark matter. Or a stripped remnant could merge with another baryon-rich object, mixing debris from different orbits into a ghostly ultra-diffuse galaxy. Expectation, clean categories. Reality, messy mergers that blur every boundary. Before we get started on what this means for cosmology, there is one crucial ingredient: environment. Systems like the NGC 1052 group, packed with galaxies and crisscrossed by tidal features, are perfect factories for these exotic remnants. Repeated encounters, overlapping gravitational fields, and a steady wind of debris make rare pathways suddenly plausible. In contrast, an isolated dwarf, drifting alone beyond major clusters, has almost no way to lose its halo or to be born as a tidal fragment in the first place. Timescales matter too. These fragile galaxies may only survive for a few billion years before being shredded completely. That raises an uncomfortable possibility. Perhaps we are catching them at a special moment in mid-disintegration, just long enough for deep surveys to notice. But the universe is vast. Even if these pathways are rare, scattered across hundreds of billions of galaxies, rare does not mean invisible. It means there should be just enough of them for the next generation of telescopes to find and to test whether dark matter-free really means what it sounds like. If those rare pathways really exist, they are not just curiosities, they are crash tests. Tonight, we're going to use them to ask a brutal question. How much can you damage a galaxy before it stops being a galaxy at all? In the standard picture, dark matter halos are not optional accessories. They are the structural frames of the cosmic city. A spiral like the Milky Way sits inside a vast, roughly spherical halo that outweighs its stars by a factor of 5 to 10. That invisible halo acts like a protective cocoon. It deepens the gravitational well, helping the galaxy hold on to cold gas against the solar system-scale winds of the surrounding environment, and it lets the whole system resist the tidal forces from nearby galaxies and the group potential trying to tear it apart. Strip away that cocoon and everything changes. Without a massive halo, the same tidal field that gently tugs on a normal galaxy can shred a diffuse one, stretching it, unbinding its stars, and peeling away its gas. No one expects a galaxy like NGC 1052 DF2, with almost no measurable dark matter, to be especially long-lived. The question becomes, how long can something that fragile survive before it dissolves into the background light of its host group? DF2-like systems probe that survival limit directly. They are laboratories for the edge conditions of stability. How spread out can the stars be? How low can the internal speeds get and still remain gravitationally bound without the anchor of a heavy halo? Simulations suggest that once a galaxy is this airy, even a modest encounter or a pass through the group's center can unbind it in a few billion years or less. By the end of tonight, you're going to understand why just finding a handful of these objects already constrains how violent their past orbits could have been. Their stars add another layer of forensic evidence. By measuring stellar ages and metallicities, scientists can tell whether these galaxies formed stars steadily over cosmic time or in short, intense bursts. A long, gentle history points to an early formed system that somehow lost its halo later. A population dominated by old, metal-poor stars hints at a rapid formation event followed by abrupt quenching. Either way, the spectrum of those stars encodes when the gas supply was cut off and how suddenly the mission of star formation ended. And that brings in one more assassin: ram pressure stripping. As a small galaxy plunges through the hot intragroup medium, the thin million-degree gas acts like a headwind. To the galaxy, that wind is a boundary it must cross. If the pressure is strong enough, it can blow out the galaxy's own cold gas, turning off future star birth even if some dark matter remains. Dark matter-poor galaxies sit right at the intersection of all these processes. They are natural experiments in extreme survival, showing how far you can push a system toward dissolution before it finally falls apart, and hinting at what might be happening to far more ordinary galaxies just beyond the limits of what current telescopes can see. So, if individual galaxies can be nearly stripped of dark matter, the next question almost asks itself: could there be entire regions of the universe where dark matter is just gone? Whole stretches of space where only normal matter roams free, like DF2 scaled up to intergalactic size. Tonight, we're going to push that idea as far as the data allows, and then watch it collapse under its own weight. On galaxy scales, DF2 and its cousins are small, local anomalies. They are to cosmology what a weird, wind-carved rock is to geology. Fascinating, revealing, but not a sign that the whole planet breaks the rules. On the largest scales, the universe is astonishingly well behaved. Galaxy clustering, the way galaxies group into filaments and clusters across hundreds of millions of light-years, lines up with a picture where dark matter is widespread and dominant. If whole megaparsec-sized regions were truly dark matter-free, that grand pattern would shatter. Before we get started on just how strict that pattern is, zoom out in your mind until the Milky Way is a dot. What appears is the cosmic web, a vast network of filaments, nodes, and voids. Simulations that include dark matter produce this web naturally, as invisible halos pull in gas, form galaxies, and link them together. Without a relatively uniform sea of dark matter on large scales, the web either never forms or looks violently different from the one telescopes have discovered. One of the sharpest tests comes from baryon acoustic oscillations, faint ripples frozen into the distribution of galaxies by sound waves in the early universe's hot plasma. Their precise scale, mapped across billions of light-years, matches predictions only if dark matter was already everywhere, shaping how normal matter clumped long before planets, stars, or solar systems existed. Large-scale gravitational lensing tells the same story. When light from distant galaxies bends around massive foreground structures, the resulting maps show a dark matter landscape that is smooth on megaparsec scales, with no giant holes where only baryons live. No one expects that landscape to be perfectly even. Clusters are overdense, voids are underdense. But those are statistical fluctuations around a very specific average density, not true deserts. If you carved out a region with baryons but no dark matter at all, its galaxies would assemble late, grow differently, and drift in ways that would tear the observed cosmic web out of alignment with the cosmic microwave background. By the end of tonight, you're going to understand that DF2-like galaxies are edge cases riding on top of a dark matter-rich universe, not cracks in its foundation. Local anomalies exist. Large-scale absence does not. Now, let's begin to ask what that means for theories that try to replace dark matter entirely. Now, let's begin to look at these galaxies the way working scientists do. Not as embarrassments, but as opportunities. In physics and astronomy, the most extreme objects are where theories go to get stress tested. The hottest stars, the densest neutron stars, the fastest pulsars, the wildest black holes. They live at the edge of the map, where the equations are stretched until something snaps. This pattern shows up all across space science. For 2 centuries, Newton's law of gravity guided predictions for the solar system, with almost eerie precision. Planet after planet, spacecraft after spacecraft, the orbits lined up, until Mercury. Its orbit precessed just a little too fast. Not much. 43 arc-seconds per century, but that tiny mismatch sat there for decades like a splinter in classical physics. The expectation was simple. Better data would fix it. The reality was stranger. No amount of extra planets or clever tweaks could close the gap. That anomaly helped push Einstein to a new description of gravity itself, general relativity. A microscopic deviation in one planet's path ended up reshaping how we understand the entire universe, from black holes to the expansion of space. The same thing happens higher up the energy ladder. When ultra-luminous X-ray sources were first discovered, they were too bright to be ordinary stellar black holes, yet too common to all be the supermassive monsters at galactic centers. No one expects a whole new population of objects. No one predicts intermediate mass black holes hiding in plain sight. But these outliers forced theorists to revisit how black holes feed, how radiation escapes, and where the boundaries between categories really lie. DF2-like galaxies sit in that same uncomfortable zone for cosmology. Standard models tie galaxies to massive dark matter halos in a tight statistical dance. Big halo, big galaxy. Small halo, small galaxy. These ultra-diffuse dark matter pore systems live out on the fringe of that galaxy halo distribution, where the usual simplifying assumptions are weakest and the solar system-style precision breaks down. Are they rare tidal wrecks, stripped by encounters with larger neighbours? Are distance estimates slightly off, making the dark matter only appear to vanish? Or are these the first hints that, under extreme conditions, gravity and dark matter might not behave exactly as expected? Before we get started rewriting textbooks, scientists demand that the data survive every possible attack. That balance between skepticism and curiosity is the quiet engine of progress. Observers push for sharper images, better velocity measurements, independent distance checks. Theorists build simulations where galaxies are smashed, harassed, and torn apart by cosmic winds and crowded environments. If the anomalies fade with better data, the mission is still a success. The theory passed another brutal test. If they persist and multiply, the theory has to evolve. Tonight, we're going to follow that logic all the way out, because in the final stretch, these ghostly galaxies force a deeper question. Are they sharpening the case for dark matter, pointing to new physics of gravity, or hinting at something even stranger about reality itself, and about our place inside this vast, invisible system that we're only beginning to understand? So, where does this leave the larger war between dark matter and modified gravity? To see why these strange galaxies matter, you have to zoom out across the entire cosmic system of evidence. Now, let's begin. For decades, dark matter has been winning on points. Galaxy rotation curves refuse to slow down with radius. Stars in spiral disks orbit so fast that without an invisible halo, the whole structure should fly apart. Galaxy clusters show the same problem at a bigger scale. The galaxies move too quickly. The hot gas is too energetic, unless there is 5 to 10 times more mass than the stars alone can provide. Gravitational lensing then draws the invisible directly, bending light from background galaxies into arcs and rings that map out enormous, unseen halos. And beyond individual systems, the cosmic microwave background locks it in. Those tiny ripples in the afterglow of the Big Bang have a very specific pattern of peaks and troughs in their power spectrum. Fit that pattern and you get a universe with about 5 times more dark matter than normal matter, plus a dash of dark energy. Change gravity instead of adding dark matter, and matching all of those scales at once becomes extremely hard. But modified gravity has its own quiet power. In many disk galaxies, a simple tweak to Newton's law at very low accelerations, like in MOND, traces the observed rotation curves with remarkable precision using few free parameters and no dark halo. The tight relation between visible mass and rotation speed, the baryonic Tully-Fisher relation, drops out almost automatically. No one expects such a clean law to emerge so naturally unless there is something deep going on. Then DF2-like galaxies walk onto the stage. In standard dark matter cosmology, they should not exist in isolation. To explain them, scientists invoke extreme tidal stripping, violent encounters, or finely tuned interactions with neighboring galaxies. In MOND, they are equally awkward. The theory predicts extra gravity tied to the visible mass, so to get no dark matter, you need special external fields, non-equilibrium dynamics, or very particular orbital histories. This is the pattern interrupt. The galaxies that look empty of dark matter are not a comfortable win for either side. They are a stress test. By the end of tonight, you're going to understand why most cosmologists still lean heavily toward dark matter as a real substance. It works from dwarf galaxies to galaxy clusters, from lensing maps to the solar system scale imprint of the early universe's radiation. Modified gravity must bend further with every new DF2-like system discovered, and the tension is growing. But this isn't a purely philosophical scorecard. It cuts into the heart of physics. Are scientists chasing new particles drifting through space, or new laws of gravity that reshape how every mission, every spacecraft, and every planet fits into the grand design of the cosmos? Before we get started on that deeper question, there's one more twist these ghostly galaxies might be hiding. That twist is this: what if there are no dark matter particles at all? What if galaxies like DF2 aren't missing an ingredient, they're exposing a flaw in the recipe? In one camp, scientists treat dark matter like a new species of particle, drifting through the space, shaping the solar system's place in the Milky Way, and silently steering planets and galaxies. In the other, gravity itself is the suspect. In emergent gravity ideas, the familiar pull between masses isn't fundamental. It arises from deeper microscopic physics, a bit like temperature emerging from the chaotic motion of atoms, and in certain conditions it mimics the extra gravity, usually blamed on dark matter. Now, let's begin with that emergent picture. In these models, the universe has hidden degrees of freedom in space, tied to quantum information or the vacuum itself. When baryons, normal matter, clump together, they disturb this invisible medium. The response looks to a galaxy like an extra gravitational halo. No particles, no invisible cloud, just modified behavior of the gravitational field that depends on how the visible mass is distributed. That sounds flexible, but DF2-like galaxies push hard on that flexibility. Here is a system where the stars, globular clusters, and gas sit in a faint, extended disk, yet the measured motions seem to follow only the visible mass. If the effective gravity is supposed to know about the baryons and automatically add a dark matter-like boost, why would that mapping sometimes turn off? How finely can an emergent law tune itself before it stops looking like a law of nature at all? There is another radical possibility. Tonight, we're going to step from particles into waves, ultra-light axion-like fields, fields with masses trillions of times smaller than an electron, can form giant quantum waves on galactic scales. Instead of individual particles orbiting, the dark component behaves like a coherent field with interference patterns, soliton cores, and halos that are naturally smooth on small scales. In those fuzzy, dark matter scenarios, the smallest galaxies are hardest to form. The wave nature washes out tiny clumps, erasing some of the small-scale structure that cold, dark matter predicts. By the end of tonight, you're going to understand why that matters. DF2 and its cousins live right at the boundary where these wave effects should be dramatic. Their very existence, and especially their apparent lack of dark mass, tests how those ultralight fields cluster, fragment, or get stripped during galaxy interactions. No one expects a handful of dim smudges on a telescope image to arbitrate between quantum waves and emergent gravity. No one predicts that 2 or 3 galaxies will overthrow decades of theory. And absolutely no one anticipates that they will do it cleanly. The data are still thin, the distances debated, the internal motions hard to resolve. But each strange system adds to a growing portfolio of small-scale challenges. Whether dark matter is a particle, a field, or an emergent phenomenon written into the fabric of space itself, galaxies with unusual dark matter content are the perfect test spacecraft, flying through parameter space and slamming into the edges of our models. The mission now is to find more of them and see which ideas survive the impact. Those impacts matter, but they don't rewrite the whole script of the universe. To see that, you have to zoom out from individual galaxies and look at the largest stage space has ever offered, the cosmic web. Now, let's begin. When supercomputers simulate a young universe filled with dark matter, something eerie happens. Out of an almost uniform fog, thin filaments grow, knots form where filaments intersect, and vast empty voids open up between them. Run the simulation forward billions of years, and the pattern of galaxies, clusters, and voids looks astonishingly like what telescopes actually see across hundreds of millions of light years. The expectation is simple. Start with the smooth glow revealed by the cosmic microwave background, where temperature variations are only about 1 part in 100,000. With only ordinary matter, those tiny ripples barely grow. There isn't enough gravity, fast enough, to turn that gentle mottling into the dense clusters and sprawling filaments mapped by surveys like Sloan. The reality is that the universe did grow that structure. Dark matter is the missing engine. By the end of tonight, you're going to understand why that engine is so hard to replace. Dark matter doesn't just help individual galaxies rotate, it starts working long before the first stars ignite. Because it doesn't interact with light or the hot radiation wind from the Big Bang, it can begin clumping early, forming invisible scaffolding. Ordinary gas then falls into those wells, cools, and lights up as the galaxies we see. This isn't just a narrative that scientists tell themselves. Precision measurements from missions like Planck, WMAP, and ground-based observatories turn the microwave sky into a kind of barcode for the entire cosmos. The heights and spacing of those temperature ripples lock in the total matter density, the fraction in ordinary atoms, and the fraction in something that behaves like cold, dark matter. Those numbers come out the same whether one looks at galaxy rotation, gravitational lensing, or the way clusters grow over time. No one predicts that a handful of strange galaxies will overturn that entire interlocking system. DF2-like galaxies are local wrinkles on an otherwise smooth cosmic fabric. They are surprising, they are important, but they sit on top of a large-scale pattern that still screams dark matter from every direction. So the mission now is not to decide between dark matter everywhere and no dark matter at all. The deeper question is, how does this invisible component interact with galaxies across all their messy diversity? Tonight, we're going to follow that thread, from galaxies drowning in dark matter to those that seem to have almost none, and see what that contrast reveals about the hidden architecture of the universe. So, if dark matter doesn't behave the same way in every system, here's the uncomfortable follow-up. What even counts as a galaxy anymore? For decades, the operational answer has been simple and powerful. A galaxy is a gravitationally bound system of stars that needs an unseen mass component to explain how fast those stars move. No dark matter, no galaxy, clean, efficient. And then DF2 walks in and breaks the rule. In NGC 1052 DF2, the motions of its star clusters match almost perfectly what you'd expect from the visible mass alone. No extra invisible halo required. The boundary between galaxy and star cluster was supposed to be enforced by dark matter. DF2 and its sibling DF4 step right over that line. Prediction versus observation again. The prediction said, every galaxy lives in a massive dark matter halo. The observation quietly replies, here is a large faint system that seems to have almost none. So scientists are forced to rewind and ask, maybe the definition shouldn't lean so hard on dark matter. Tonight, we're going to look at the alternatives. One option is size. You could decree that anything above a certain physical scale in space, say a few thousand light-years across, is a galaxy. DF2 passes that test easily. It's as wide as the Milky Way's bright disk, just far more diffuse. Another option is stellar mass. Set a threshold in solar masses and anything above it joins the galaxy club, anything below becomes a cluster. But those simple thresholds hide deeper complexity. Many dwarf galaxies have the same stellar mass as massive star clusters, yet they host multiple generations of stars, different chemical abundances and extended structures. They look and behave like miniature versions of full-scale galaxies. DF2 again lands in the grey zone. It's large, ultra-diffuse, and its stellar population shows a history more complex than a single burst. By the end of tonight, you're going to understand why that complexity matters just as much as size or mass. This is where new categories start to creep in. Maybe systems like DF2 are baryonic galaxies, dominated by normal matter with only a trace halo, or halo-less remnants, the shredded survivors of violent interactions that stripped away their dark matter. No one expects a tidy vocabulary to survive first contact with reality. No one predicts that a handful of ghostly smudges around another galaxy will force a rewrite of the glossary. And this isn't just semantics. How you label DF2 changes how surveys are designed, how simulations of galaxy formation are compared to data, how galaxy counts are tallied across cosmic time. Call DF2 a galaxy, and you admit that dark matter is not a defining ingredient. Call it something else, and you risk hiding a crucial clue in a side category. The language shapes the mission. Now, let's begin to push this to the limit. If dark matter-poor galaxies are redrawing the boundary lines, what do they reveal about the hidden scaffolding that still seems to hold the rest of the universe together? Those strange, pale smudges on deep images are not just galaxies, they're a live demonstration of how science actually moves, not in a straight line, in loops. The cycle begins with a surprise. A team measures the motions of star clusters in NGC 1052 DF2 and finds that, at the assumed distance, they move exactly as fast as the visible stars predict. No extra pull, no hidden halo. The claim lands with a jolt. This galaxy has little to no dark matter. In a universe where dark matter is supposed to be the invisible backbone of the cosmic web, that sounds like saying a planet orbits the sun with no gravity. No one expects a result like that to pass unchallenged. Within days, other scientists are checking every step. The distance to DF2, the way the velocities were extracted, the statistical treatment of a tiny sample of star clusters. The bold headline number is only the tip. The real argument happens underneath, in the methods, the assumptions, the error bars. Here is where uncertainty becomes a character in the story. Change the distance by a few megaparsecs, and the inferred mass of the galaxy and its dark matter content swing dramatically. Widen the error bars on the velocity dispersion, and no dark matter can turn into low dark matter, or even normal within the same data. The mission is not just to measure the universe, but to understand how trustworthy each measurement really is. Then comes the pattern interrupt. New eyes on the same patch of space. Independent teams point different telescopes, use different instruments, and remeasure DF2, its sibling DF4, and other ultra-diffuse galaxies. Some analyses push the distance closer, inflating the apparent dark matter. Others confirm that even with more conservative assumptions, these systems are still oddly light on the invisible component. The boundary between impossible and merely weird shifts. From the outside, this can look like chaos. One year, headlines say, dark matter is dead. The next year, revised distances say dark matter is fine. But from the inside, this is the solar system-wide machinery of science doing exactly what it is designed to do. Claims are proposed, attacked, defended, revised. Changing one's mind about DF2's distance or its mass is not a failure of the model. It is the model breathing. Tonight, we're going to treat that flexibility as a feature, not a bug. Frontier results live near the edge of what our spacecraft, telescopes, and detectors can reliably see. No one predicts that the first interpretation will be the final word. Absolutely no one anticipates that the first error bars will capture every hidden systematic. And the story is still unfolding. Future observations may show that tidal encounters stripped these galaxies of their halos, or that they were never dark matter rich in the first place, or that the entire framework needs to be bent again. By the end of tonight, you're going to understand not just what dark matter does in space, but how galaxies like DF2 mark the strange boundary where our theories almost break, and where the next mission begins. Now, let's begin tying this all together. We started with dark matter as the invisible skeleton of the cosmos, the hidden framework that lets galaxies form, spin, and survive the relentless pull of gravity. In that picture, every galaxy is wrapped in a massive, unseen halo. Then, suddenly, telescopes pick out ghosts like NGC 1052 DF2 and DF4, faint smudges in space whose stars move as if that skeleton is missing. No one expects the universe to casually throw those onto the stage. To see why, you learn to read the motions. In normal galaxies, stars and gas orbit too fast for the visible mass alone. Their rotation curves stay flat where Newton says they should fall. That mismatch is how scientists infer dark matter, or in MOND, how gravity itself bends at low accelerations. But in DF2-like systems, the internal speeds of star clusters and planetary mass tracers match what the starlight alone predicts. Prediction versus observation flips. The gravitational pull seems to come almost entirely from the visible mass, and that shocks both the dark matter camp and the modified gravity camp at the same time. Tonight, we're going to remember just how many escape routes theory tried to build. Distance could be wrong. If DF2 is closer than first measured, its true mass and size shrink, and the no dark matter claim evaporates. Measurements could be biased. A handful of bright clusters might not trace the whole galaxy, or hidden orbital motions could inflate or deflate the inferred mass. Non-equilibrium dynamics add another layer because if a galaxy is being torn apart, its stars may not follow simple, steady orbits at all. Then come the more dramatic scenarios. Tidal stripping in a crowded group can peel away a galaxy's dark halo first, leaving a puffy, ultra-diffuse remnant that is temporarily dark matter poor. Tidal dwarfs can form from the shredded tails of bigger galaxies inheriting gas and stars, but almost none of the original halo. And rare environmental histories, multiple close passes, repeated encounters with a massive neighbor, motion through a dense, hot medium, can push a galaxy to the very edge of what simulations predict. No one predicts these outcomes to be common, but absolutely no one anticipates that they must be impossible. Right now, the balance of evidence points in a specific direction. These odd galaxies probably are real denizens of the cosmic zoo, rare products of extreme interactions in dense systems, not clean proof that dark matter doesn't exist. If anything, they highlight how the same dark framework that shapes most galaxies can, under the right conditions, be rearranged, stripped, or never fully assembled. By the end of tonight, you're going to understand not just the headline, claim that there are galaxies with no dark matter at all, but the tools used to weigh them, the caveats that haunt each measurement, and the deeper stakes for cosmology. You now see the boundary where simple pictures fail, and in the next section, that sharper universe is going to push back even harder. That sharper universe is not just a playground for distant galaxies and exotic theories. It reaches straight back to you, to the question of why there is anything here to wonder about in the first place. Dark matter sounds abstract. Invisible halos, velocity dispersions, gravitational lensing arcs at the edge of a telescope's field. But underneath all that technical language is a very simple human impulse to understand what the universe is made of and how it works at the deepest level. The same drive that once mapped the planets of the solar system is now aimed at the unseen scaffolding that holds galaxies together. Think about the Milky Way as a whole mission. The standard picture says a massive dark matter halo formed first, then pulled in normal gas, which cooled, fragmented, and lit up as stars. No dark matter halo, no stable galaxy. No stable galaxy, no long-lived stars, no long-lived stars, no time for planets and chemistry and life to assemble. In that view, dark matter is not an astrophysical footnote. It is part of the precondition for you sitting here, listening to a video about galaxies drifting through space. That is why a galaxy like NGC 1052 DF2 hits so hard. If its stars really move exactly as their visible mass predicts, with almost no extra gravity from a hidden halo, then one of two things must be true. Either dark matter is more flexible than expected, able to be stripped and rearranged in ways simulations only barely hint at, or the entire story about how galaxies form and survive is missing a crucial chapter. No one expects a handful of faint smudges to threaten the dominant cosmological model, yet here they are. At the same time, anomalies like DF2 are a reminder that theories are not sacred, they are tools. They work until they don't. The boundary between established and mysterious is not fixed. It moves every time scientists discover an object that refuses to fit. No one predicts that a tiny shift in distance estimates or a subtle bias in velocity measurements could flip a galaxy from impossible to perfectly ordinary, but absolutely no one anticipates that all such anomalies will simply vanish either. So, where do you stand? If a bet had to be placed tonight, would you say dark matter-free galaxies are real objects carved by violent interactions, or observational illusions waiting to evaporate as data improve? There is no safe answer yet, only probabilities and preferences. Tonight, we're going to treat that uncertainty as an invitation to imagine future spacecraft, sharper telescopes, and new minds, possibly yours, pushing beyond the current boundary of what is known. Now, let's begin to turn that curiosity into action and connect you with a community that lives for questions exactly like this. So now, come back to that first image, a pale, ghostly galaxy drifting through space, its stars gliding along slow, measured orbits, as if no invisible halo surrounds them at all. No extra pull, no hidden mass, just light and gravity matching perfectly, a quiet rebellion against the rules every textbook in the solar system says the universe should follow. Set that single rebel beside the larger reality you now understand. On the grandest scales, dark matter shapes the cosmic web, pulling galaxies into filaments and clusters, setting the boundary between empty voids and crowded cityscapes of stars. The planets in our own system trace neat paths because a massive sun anchors them, but galaxies dance to a deeper rhythm, one driven by a dark scaffold that, in almost every case, outweighs their visible matter by a factor of 5 or more, designed as a simple ingredient to fix rotation curves and galaxy motions. Dark matter became the backbone of modern cosmology. And yet, in a handful of ultra-diffuse galaxies like DF2 and DF4, scientists discovered motions that seem to say, "Not here." The stars drift slowly, the velocity spread is tiny, and the usual dark halo appears to be missing or stripped away. No one predicts these outliers. Absolutely no one anticipates that a theory built to explain everything would be challenged by a few dim smudges on a deep exposure. Tonight, we're going to leave those smudges hanging in your mind as more than anomalies. They are questions sharpened into galaxies. Are they illusions caused by distance errors and tricky starlight, or fossils of violent tidal encounters where the dark halo was torn away and left to drift beyond the frame? Each possibility forces the mission of science to adjust, to refine, to admit that nature writes a more complicated script than our neat diagrams suggest. By the end of tonight, you're going to understand one more thing. Progress in science is not the moment when every answer locks into place. It is the moment when the right questions come into focus. How many of these ghostly systems are out there? What hidden wind of interactions sculpts them? And what does it mean if in rare pockets of space galaxies can exist without the invisible glue they were supposed to need? Carry that mindset with you beyond this video. In your own life, the world will offer rules that feel universal, assumptions that seem as solid as a dark matter halo. Before we get started on any new belief, it is worth asking, what if there are quiet exceptions hiding in the data? What if the structures that really shape events are invisible at first glance? To understand anything deeply, from a relationship to a career to the universe itself, you have to be willing to test the edges. to look for the places where expectation and observation quietly disagree. So let the final image linger. A field of dark, star-strewn space. A few fragile galaxies suspended on nothing that you can see. The boundary between what is known and what is still only guessed at fading into black. The camera pulls back, the light drains away, and somewhere out there, another faint smear of stars may already be waiting to overturn the next beautiful theory. So tonight, somewhere far beyond our solar system, those ghost galaxies are still drifting. The stars inside them are still moving slowly, gracefully, without the invisible halo that almost every other galaxy in the universe seems to need. The data is patient. The motions do not change because we are looking. The universe does not care whether our textbooks are right. There is something deeply calming about that. The cosmos keeps its own ledger. Dark matter, if it exists, will keep doing what it does in the trillions of galaxies that need it, and the small handful that seem to manage without it will keep gliding through the dark, waiting for the next generation of telescopes to either confirm them as genuine rebels or quietly fold them back into the standard picture. Sleep well tonight, and tomorrow we will continue to explore the deepest mysteries of the cosmos together.